Okay, part two of the Michaelis-Menten kinetics. Now, we're not talking about Michaelis-Menten per se. We're talking about variants of Michaelis-Menten, or really just other mechanisms if you want to think of it that way, but these are in some ways at least similar to Michaelis-Menten. And they give rise to somewhat different behavior, but as I commented before, surprisingly, somewhat surprisingly anyway, not that different. All right, so let's look at these cases. The first one is, and perhaps maybe the most interesting in the larger context for this section, is the idea that instead of the irreversible standard Michaelis-Menten mechanism, we add a backward step to the product formation step, which makes the entire mechanism reversible from one end to the other. So now, if we had some product, and let's say we had zero substrate to start with, the mechanism looks like the Michaelis-Menten mechanism, but going backwards, right? Product would become substrate, and you'd produce product would be put in, and you'd produce substrate at the end. And so this is a fully reversible version of Michaelis-Menten. Usually in the experiments that measure enzyme kinetics, you put in substrate and you don't wait for product to build up. So the reason that Michaelis-Menten is usually chosen to be irreversible is that there just isn't any product around. It isn't so much that this backwards reaction doesn't exist, it's just there's no rate for it because there's no product. But if you allow for product to build up, or if you put some product in to begin with, or if you're in some situation where you just don't have control over whether there's product present or not, then this reversible version can be important. We can derive it the same way we derived Michaelis-Menten, and if you do, I won't go through it because it's not that interesting, but if you do, then here's the rate expression that you get. It depends now on two different substrate or two different species concentrations, one for the substrate, one for the product. And now instead of there just being a Vmax, there's a reverse Vmax. And instead of there being just one Km, there's a reverse Km. And you can see that the definitions of everything, all the four quantities now, are the same as they are for regular Michaelis-Menten, except that wherever there's the forward value, you put in the equivalent thing for the backwards reaction. In other words, for example, K2 here is the rate constant for the second step going forward. K minus 1 is the equivalent one for the reaction going backwards, and so K minus 1 is what appears here. And likewise, if you look at Km and Km prime, actually I have a drawing down here, you can see that Km prime is the same thing as Km for a reaction that's going backwards. Also, for this reaction, if you wait long enough, or if you're under the right conditions so that the velocity goes to zero, you can go to equilibrium, and in that case, it should be that this mechanism gives us the equilibrium constant for the overall reaction, right? The overall reaction is, well, I didn't write it down here, I wrote it down in the last set of notes, but the overall reaction is S goes to P in both directions. In that case, the equilibrium constant should be the equilibrium value of P over the equilibrium value of S. And if you just set this to zero and solve for what you get, then from Michaelis-Menten you get this combination of forward and backward parameters. And after a little bit of algebra, that boils down to just K1 times K2, where K1 and K2 are the equilibrium constants for this first step, that's K1, and K2 is the equilibrium constant for the second step. So it's just like, it just follows the rules exactly like they should for a general reaction. If this is the first reaction and this is the second reaction, then K1, K for the overall reaction should just be K1 times K2. And that's in fact what you get. So the reversible Michaelis-Menten is in some ways just the sort of full Michaelis-Menten case. The fact that Michaelis-Menten is normally considered to be irreversible can be thought of as sort of a special case of this more general case. All right. Another possible mechanism is one where instead of just one substrate, the overall reaction, just one substrate, you have two substrates that are coming together to form a product. This is obviously very common. Enzymes frequently have two substrates because very frequently what an enzyme does is put those two substrates together to form some new product. So what do you do in that case? Michaelis-Menten only has one substrate. Well, now you've got a more complicated mechanism. In this particular case, you've got a sequential case. You have a case where the enzyme binds the first substrate to form an enzyme-substrate complex. And then the enzyme-substrate complex binds the second substrate to form a double enzyme-substrate complex. And then finally, these two guys both react on the surface of the enzyme to release the enzyme and produce a product. In that case, it turns out that the rate law depends on both substrate concentrations, and also that there are two Km-like values, but the first one is just the Kd. So it's not a Km, it's just K minus 1 over K1, which is in fact the Kd for this first reaction, thought of as a binding reaction. The second quantity or parameter is Km2, which is a lot like just a standard Km from normal Michaelis-Menten kinetics. And now you can see again you get this more complex expression that depends on a Kd value, a Km value, and then another value in between that isn't really either of those. Here's all the definitions of them. And so you get a much more complicated expression, but you can derive it using the standard methods that we used for Michaelis-Menten and that we've used throughout the whole section on kinetics and especially catalysis. We set the velocity equal to, our definition of the velocity is the rate of production of the product, P, as usual. And then we apply the steady state approximation to all the intermediates. But in this case, look, here's an intermediate, here's another intermediate, so there's two intermediates, and you apply the steady state approximation to both of them. Use the steady state approximation to eliminate those intermediates, and that's where this rate law expression came from. Much more complicated, as I say here. However, if you hold one of the substrate concentrations constant, and then do some algebra, then you can show that the substrate, that the rate law behaves like Michaelis-Menten, and if you were to plot it, you'd get a Michaelis-Menten-like curve. But the new velocity, the new values for Vmax and Km would depend on the substrate 2 concentration and all these other things. In other words, they'd be much more complicated expressions and different values than what you'd get from the standard Michaelis-Menten mechanism. A third example is the so-called ping-pong reaction. This is a case also where you have two substrates, but also producing two products in this case, not a single one. So we're getting more and more complicated as we go along. Here's the mechanism. Probably some of you have at least heard of it. There's a ping step in which the enzyme binds the first substrate to form an enzyme-substrate complex. The enzyme-substrate complex then reacts to form product number 1, but it also creates an altered enzyme. So the enzyme doesn't have a substrate on it anymore, But it's not the same as the original enzyme. Oftentimes what this means is that the first substrate, say, bound something to the first enzyme or changed its conformation into some sort of activated form. In some cases, for example, the first product phosphorylated the enzyme, so this E star would be a phosphorylated version of the original enzyme. In other cases, it's forced it into a new conformation that it wouldn't normally go into, so it's sort of cocked a spring in that case. Anyway, this now activated enzyme binds to a second substrate and forms another enzyme substrate complex. And then the second enzyme substrate complex goes on or reacts again to form the second product and releases now a normal original version of the enzyme. So you got to go, that's the Pong step. You got to go through two steps or two parts of a cycle before you get back to the original enzyme. Again, the same procedure. You define, in this case, the rate of reaction to be the rate of production of the second product, and you apply the steady state approximation now to three different intermediates, right? This is an intermediate, this is an intermediate, and this guy is also an intermediate, and so it gets increasingly complicated. You can write the rate expression in this form, and it's hard to because you've now got two substrates and several different Km type values, as well as a Vmax type value. It gets harder and harder to understand what this means, but we can choose a simple special case. Suppose both substrates have the same concentration. Of course, this is not generally the case, but we can always investigate this special case. And suppose all the K values are also equal to each other. In that case, the expression above reduces to this one, which looks just like standard Michaelis-Menten, except that the denominator is squared here instead of just being to the first power. So I call it mm squared. And in that case, the velocity versus substrate curve would look something like Michaelis-Menten, except that there's, at low concentrations of the substrate concentration, there's a bit of a turn on. You have to go to somewhat higher values of the substrate concentration before you start getting appreciable velocity. Also, the point at which the substrate is equal to the Km value occurs only at 1/4 of the value of Vmax, because you can see that if this is equal to a 1, you've got a 2 in here, but then that gets squared, so you've got Vmax over 4. So there are differences. Anyway, that's all I want to say about these variants. The next thing we'll talk about after the exam is enzyme inhibition, which is probably more interesting generally.